welcome everyone. Again, I'm Merlise Clyde, and I was asked to kind of give this overview talk on model uncertainty and uncertainty quantification. I apologize for any of you who were actually at the SIAM meeting earlier in this year. Is this working? No. Now? Okay. So this will have an overlap with some of that, but for the rest of you that are here for an overview, then I hope that this will enlighten some of the discussions and ideas for working groups later in the conference. Okay. So if you think about what's uncertainty quantification, I'm sure everyone in the room here probably is coming perhaps from a slightly different perspective. So from just Wikipedia, this is the science of characterizing, quantitative characterizing and reduction of uncertainties. There can be lots of uncertainties, okay? So from a statistician, we might have a model, and so there are parameters in that that are unknown, okay? And so we might want to try to quantify our uncertainty about the parameters that are there. We might have inputs, so if we're thinking about computer models or other types of regression models. Often when we're actually using models, we may have to approximate them, so there may be algorithms that are used to learn the models. So if you're Bayesian, you might be using Markov chain Monte Carlo. That may induce some other uncertainties into the problem. There can be experimental uncertainty, so that is if we have a kind of response that we're interested in. So if climate models, we might be interested in temperature. Well, we may not be able to measure things exactly, and so there may be uncertainty that's induced just through the measurement process of gathering data. Okay. And then one of the things that I'll try to focus on is what we might refer to as model uncertainty. And so that can be the structural uncertainty about how the data are used to generate the responses, so more or less about that model generating process. And then last, we may be concerned about predictive uncertainty. That is, we might want to use these models for making predictions at some future time. This might involve extrapolation or even interpolation, so some given inputs. Again, those inputs also might be measured with error. So these are some of the different aspects of uncertainty that come into play from at least the statistical perspective, and then also perhaps from the mathematical in terms of some of the algorithms. Okay. And so if we think about predictive uncertainty, we can kind of decompose this into there's parts of reducible error. Those are things that we can, through collecting data or refining the models, we can actually try to reduce, but then there are the other things that we just cannot control. So the irreducible error, again, in terms of like measurement variation, some of that we may not be able to reduce, even with smarter designs. Okay, and so that kind of gets back into the unknown unknowns and known unknowns, and so that there's certain aspects of the model or certain aspects of the process that we may never be able to actually know. For the things that are known, we can actually try to work on reducing those in terms of our uncertainty quantification. So I'm going to focus in this talk more on the aspects of model uncertainty and how that might interact with the uncertainty quantification. And so in general, we might have a collection of models that we're entertaining. So M would be the subscript of a particular model. And so each model, to start, is going to correspond to a parametric, although it might be infinite dimensional if we're thinking about certain stochastic processes, but it provides a distribution for the data Y. Okay, so those are the kind of responses that we're interested in. And so for each of these, there may be parameters, theta M, that are particular to that model, and so that then describes kind of the structural model that we're interested in. So, and this gives a distribution for that, the data that we may be measuring with error under the model. Okay, and so one of our objectives might be to try to get predictive distributions for future observations Y, so I'll denote star for those future observations, given, say, the inputs X star and the other data that we've already observed. Okay, and so again, just kind of without loss, I'm going to just drop the dependence on those inputs for right now. We'll be conditioning on all of those. Okay, so multiple models. I've lived here in North Carolina for many years, and so one of the things that we have to worry about, generally this time of year, but this week should be great, are hurricanes. Okay, and so if you're a fan of the National Weather Service, you start to look at what the predictions are, and so often, many days out, there are multiple computer models that may be giving predictions. They have different paths. what do? Do you just pick the winner? Do you try to use some ensemble, which are often reported? But also, what about uncertainty quantification? Okay, so maybe we have a good idea of where the target is. Do we know what the bands are? And how should we combine the different models to come up with predictions? So if you're interested in risk assessment, you may want to know so many days out, what is the probability of being, say, in the region where it's going to be hit. Okay. Right. And so you'd like to be able to use these multiple models for making inferences, learning about them, maybe learning which ones are better, but also for, again, making predictions, but also, again, including that uncertainty in the aspect of those predictions. Okay, so I'm going to focus here on some of the kind of Bayesian perspectives on model uncertainty, and I'll touch on where they overlap with some of the frequentist ideas. But there are kind of three main viewpoints if you're a Bayesian when you look at model uncertainty. So the first is, say, what might be viewed as the M-closed perspective, and this idea is that out of that collection of models that we had, that true data-generating model is one of the models in that list. Of course, it's unknown. We don't know which one's the truth. That's why we have model uncertainty. But at least we have a very nicely described universe that lists all the possible models that are there. Okay. Now, that might be somewhat of a fantasy, but it is a starting point at where we might start to think about the model uncertainty. Okay. Now, incomplete is another viewpoint where it says that, yes, there is a true model, just like there might be a Santa Claus, but it's not included in the model list M. Okay? So we have a list of other models that we would like to use, okay, but the true model is actually not going to be one of those. So these other models might be proxies for the truth. And so these other models might be simpler to use. They might be easier for calculation. They might be easier to communicate to others. And so as an approximation, we would like to try to incorporate all of those in building a model and then quantifying uncertainty about that, knowing that we have the true model that's there in our pocket that we'll reserve. Now, the M-open is probably the more realistic setting. So we know the true model is not in M, but we can't actually specify the explicit form of it because it's either too difficult conceptually. Okay, we can't specify all of the interactions or components that go to it. We may lack the time to do it. We may need to have a solution rather quickly, or we do not have the expertise. Okay, and so often in terms of, again, even computer models, while they may be very, very sophisticated, they may not be able to capture all of the reality, and yet so we would still like to be able to use them. So I'll just start with we'll start with the kind of the fiction of the M-closed perspective. That still works well in many cases, but we'll talk about some of the limitations and then go on into the more realistic cases. So if we were going to try to address uncertainty from a Bayesian perspective, well, for a Bayesian, everything that is unknown, we would express that uncertainty about it using some prior distribution. Okay? And so that would allow us to kind of assign some belief or degree of belief about whether each model is the true model. We would need to specify distributions about all of the parameters that are in that model that would characterize their uncertainty a priori. And then Bayes' theorem, again, is more or less kind of our formula here. We can turn the crank and then out. At the end, we can get a posterior distribution for each of the models given the data. And so that more or less is by taking kind of the distributions or likelihoods of the models conditional on of the data conditional on the model, weighting them by these prior probabilities, and then renormalizing them to sum to 1. Okay, so now this marginal distribution, you'll note, doesn't involve any of the unknown parameters. Okay? And so again, parameters often may be used as a device to specify models, but what we're really interested in is kind of what are these predictive distributions of the data under that model. Now this involves integration over those parameters, and so that's one of the tricky aspects of trying to implement this in many problems. Okay. But once we have that, then we can get the predictive distribution for new data conditional only on the observed data by, again, this weighted average, where now we have the predictive distributions of for the data under each of the individual models, but now they're going to be weighted by our updated beliefs about those models given the observed data. Okay, and so again, these predictive distributions, there are no parameters there. We've integrated those out. With respect to the uncertainty, here at the bottom, we've got the posterior distribution about those unparameters given the data in those model specific, under the specific models. Okay, and so this, in terms of employing this, we need to be able to do often high-dimensional integration, and we also need to be able to actually carry out those sums over potentially a large number of models. Okay, so those are some of the computational challenges, but there's been a wealth of research that's looked at that in a number of key problems. Okay, so now if we're going to actually think about like estimation or prediction, so we have that posterior distribution that would summarize all of our uncertainty up to this point. But if we want to, say, report, say, an estimate, well, we could consider, say, prediction or estimation. If we were to adopt like a squared error loss, sorry, then we might consider using kind of a decision theory perspective. And so this function u is going to represent the utility of taking, say, a particular action A when the true state of nature, say, is y star. Okay, so for squared error, that would just be again, the squared difference. We'll take a negative to convert this from a loss function over to a utility function. Okay, and so if we do that, then from a Bayesian perspective, the optimal thing to report will be the action that's going to maximize the expected utility given our observed data. And so again, this is going to be taken, if we're thinking about prediction, this is going to be taken with respect to that predictive distribution of the future data given our observed data. So if we're thinking about predicting into the future. Okay, so in principle, then we can solve this. This would lead to the posterior mean. And actually, if we're in that context where that predictive distribution was actually formed under model uncertainty, then the optimal action would be to report that predicted mean, which, again, if one goes to the algebra, that is going to be that weighted average where we've got the predicted means under each of the models, but now those are weighted by the posterior probabilities. Okay, and so this uses the joint posterior distributions on both beta and m. We can also use that to obtain prediction intervals. Okay, so we can come up with optimal intervals that way. And it would allow kind of a full propagation of all of the known uncertainties. Okay, so we've been able to specify all the possible models. We've described prior distributions. We have all of the kind of the exact models, but yeah, that never happens really, okay, that we can specify all of those known certainties. Now, there's extensive literature on this, so at least in terms of regression or generalized linear models, there's a lot of work that describes the kind of prior distributions that one can use with this. There's lots of software that's available for that, so in nice problems, they're kind of closed solutions for handling this. For more complex models, then people often revert to using what might be called a reversible jump Markov chain Monte Carlo, and again, that involves a lot of kind of computational art in trying to get those to work well in many problems. There's been a lot of work on sequential Monte Carlo, so other types of kind of importance sampling, other ways to kind of approximate these averages, or there's also been more recently work on ABC, so approximate Bayesian computation, and so even like one of the previous SAMC problems was looking at that in the context of astrostatistics, and so we're trying to identify models. Again, many of those are based on more complex differential equation type models for radial velocities. Well, a simple toy problem to kind of illustrate where some of these things can fall apart, okay? And so just kind of caution in how we build these list of models. So you might think, just very simple case, we only have two models, okay? And if we think about the models, there's model M1, just involves, say, x1. Model 2 involves only x1, x2. What if the true model is actually just, it involves both x1 and x2, okay? But now in our toy list of the models that we thought we could use to kind of approximate this, well, our Bayesian model averaging under this M-closed perspective, its predictive distribution, or its predictive mean, will be a weighted average where this first part, this beta 1 hat, would be the estimate of beta 1 that we get by just using model 1 alone. The beta 2 here will be the estimate using just model 2. And you might think, well, this combination looks like it should be able to recover the truth. Well, it doesn't. Okay, and so the problem is that if we don't use a rich enough set of models, these Bayesian model averaging weights will actually converge to one for the model that's closest to the true model in Kolbeck-Leibler divergence. Okay, and so if we're going to try to employ this approach, we will need to end up using perhaps, say, a richer class of models. Okay, and so what this means is that if we have enough data, okay, and so this is an asymptotic argument, it might be fine in practice where we never get to go visit asymptopia, but in asymptotic situation, the Bayesian model averaging is only going to use the predictions from that one model that's closest to the true model. Okay, and so this is something where it might seem that by combining these models in this way, that it would be kind of a panacea, it would be able to solve our problem. So maybe we have one model that just tells us about clouds, we have another model that tells us about oceans, and we think that'll save us. We'll combine them in this way, but it won't. Okay, so we need to actually be able to build a richer set of models. Now, this would actually then, in this sense, in this case, if these two models that we're combining aren't rich enough, we will not get consistent estimates. So even if we have enough data, we will not be able to actually get consistent point estimates or distributions there. So that's a little bit worrying, okay? But again, okay, this is the case. I believe that these are my only two models, but the truth is actually something more complex, okay? And so it's just kind of as a caution when we think about building these that we shouldn't limit the models that we use if we're going to try to take this closed form for model averaging, because again, we've made that very strong belief that the true model is in the list of models. Okay. All right, so what are some potential solutions? Well, you know, of course, obvious thing in that case is let's just add a third model to that list. Okay, and so now the true model is actually in our list of models. Everything there under nice regularity conditions, priors, we will get consistency. That will be great. But how do we ever know that the true model is in our list? Okay, well, we could start to build more complex models. So we could look in terms of expanding. So if we think about models, we might think of stochastic expansions. We might use, say, over-complete representations. Dictionaries. Now then it becomes much more tricky in terms of how we embed that into the other model averaging framework, because now we have potentially more models than there are atoms in the universe. Okay. But some of those that have been successfully used, kernel regression, so I've done work with Robert Wolpert here in Levy processes. So again, it's kind of stochastic expansions. Boosting BART, so Bayesian additive regression trees. I think Ed George will be talking about that later. Again, these are other kind of ways of thinking of having a much expanded or richer set of building blocks to build the models in there. Okay. Again, so these are fairly flexible. Non-parametric are often infinite dimensional models. And so by expanding that kind of the class of predictors that might go into a model, we can kind of overcome some of that. But it's, again, there's still many of these models. There are theoretical questions about their properties. There are computational challenges because now we're working with much higher dimensional spaces. And again, the choice of priors in terms of making sure that we actually do have consistency. So it's kind of putting us back into the P bigger than N framework where we have maybe more predictors than there are observations. So you have to be very careful about kind of regularization and model fitting when we take that approach. Okay. And so, but you might think about, well, is this the only way to go? So at the beginning we said, well, there's the M open, M closed, M complete. What about other ways of trying to use these multiple models in an ensemble? Okay. Okay, so we could also go back, so we talked about our point estimate as kind of a decision problem. We could think about the problem of combining models actually as a decision problem and not as part of the model building. Okay? And so in both of these, in the incomplete or M-open perspectives, there's the explicit view that the true model is actually not in the list of models. And if that's the case, so if you're Bayesian, if you know that the true model is not there, you would not assign a prior probability to any of the models in the list. A priori, you know they're wrong, okay? And so in that sense, you would give them, say, a prior probability of 0. So that M-closed idea of where we assign prior probabilities to models would fall flat, okay? So we would be giving all those models prior probability zeros. Okay, now George Box, paraphrase, is that all models are wrong, but some are useful. Okay, and so even though those models we may not believe that they're the truth, we might still want to be able to use them because it's the best things that we've got. Okay. All right, and so you might formulate now, if we go back to kind of the action that we're going to take, is to think about, well, I've got these predictions from my potential models. Okay, I know they're not going to be perfect, but maybe what I'd like to do is to still take some weighted average or use some ensemble of them to come up with, say, a prediction and expand that to other decisions. Okay, and so the idea is now to treat the weights that we're using in combining these predictions as part of the action space. So these are things that we're going to determine rather than as one of the unknowns. Okay, so under the M-closed perspective, those weights were model probabilities, and so we were learning that. That was part of the state of nature, okay? And so part of that distribution for the data. In this case, what we would do is to say, well, I want to learn kind of optimal weights. That's part of my decision problem, okay? So it's not only that I need to make a prediction, I need to learn what weights I want to give to these multiple models. And again, we can still take this kind of Bayesian decision theoretic approach and to say, well, I want to try to find the weights as part of my action that will maximize my posterior expected utility. Okay? And so again, we can write that down. Now, whether we can solve it, okay, that's always another issue, but at least we can frame the problem in that way. Okay, so again, for negatives, say squared error as kind of a utility, and then again, we're looking at, again, trying to minimize this quantity. And again, this is an expectation with respect to the predictive distribution for future data, given the data that we've observed, but under that true generating model. Okay? So we're not going to actually use the predictions from it. We're going to use these proxy models, but we're going to use that model to help us evaluate what the weights that we would give for this other ensemble. Okay. So I'm going to focus on the M-open case because that's probably closer to reality, that we really don't have a good specification or handle on the true model. Okay. So the problem there is that we don't have an explicit form for the predictive distribution under that true model in that case. Remember, the M-open was the case where we just didn't have the expertise or time to actually get our hands on the true data generating process. Okay, so one approach, and this goes back to Bernardo and Smith, Key, Paricci, and Smith, is the idea is to partition the data, and so we might think about I've got data that I've left out, so minus J, so J might be observations that I'm going to use for my model building. Minus J are observations that I'm leaving out. And so we can think about, say, the y sub j as being proxies for those future observations. Okay, and then the sub j, this will be our kind of proxy for the observed data. And the idea is that if we do, if we randomly select these partitions, then under some weak conditions, this kind of Monte Carlo average will converge to that expected utility. Okay, and so this idea of kind of cross-validation or k-fold cross-validation could be used to kind of approximate this, our expected loss here, okay, or our expected utility. Okay, and so again, the idea is here is to try to use kind of this cross-validation as a way to justify these leave-out samples to kind of approximate this posterior expected utility under this M-open perspective. Okay. There are other approaches that have looked at this more as a Dirichlet process model for estimating kind of an unknown distribution function. And again, if we there's a single leave-out case, but again, this provides kind of this justification for trying to partition the data in such a way to approximate this expected utility when we can't get our hands on the actual M true. Okay, so if we think about that now, now if we can formulate this as an optimization problem, and so under that approximation, so we've got our left-out data. In this case, I'll just use a single observation. So our goal now is just to try to find the weights that will allow us to create this ensemble of models for the prediction. Okay. And one of the things that if you just throw a bunch of models into this, and this actually goes back, there's a connection back to stacking from, again, it's a different Wolpert, not Robert, but stacking had been introduced, and Bryman had looked at this back in the, again, 90s. But the idea is if we just have completely unconstrained weights, well, this can become very unstable. And so kind of original solutions would be to say, well, if we think about these weights, you might think of it from a Bayesian perspective. It's like, oh, well, this kind of looks like model averaging. Let's try to constrain the weights to sum to 1, and let's try to have the weights be non-negative. Okay? The stacking argument really was just like, okay, this works. Okay, it wasn't really based on any kind of real principles of why the weights should have this type of structure. But one can actually think about this in terms of a constrained optimization as again, here we've got constraints. We can represent this as one single kind of function that we're trying to optimize. And so we can have penalties in terms of the deviation of the weights from summing to 1 and then their non-negativity. Now, with the weights here being greater than or equal to 0, that might look a lot like lasso type constraints. Okay, so if anyone's done penalized regression, except for in the coefficients in the lasso could be negative, this is going further. It says that they all have to be positive. Okay, and so, but it does have this kind of same flavor as other high-dimensional regularization methods that are used in statistics. Okay, so comments on the solutions. So in nice problems, you can actually work things out analytically. And so with the sum to 1 constraints, the weights are basically, if this E here, this is kind of a matrix of residuals. Okay, so we have the different models predicting each of the left-out observations. Then the weights here are going to be proportional. If we take the E transpose E, we look at the inverse of that, and now we force them to sum to 1. And so one can think about this, if residuals were all uncorrelated, basically that E transpose E, the diagonal, those would be the mean squared errors for predicting using that model. Okay, so if this ends up being kind of inverse, the weights would be inversely related to that cross-validation mean squared error. Okay, so that would be the case where we have uncorrelated residuals from the model predictions. Now that typically isn't the case, and so that's where if you have highly correlated predictions, those residual weights may be negative and highly unstable. Okay, so again, it looks like a least squares problem without that, without the non-negativity constraint. Okay, so those non-negativity, those lasso-like constraints, basically making sure that they're all greater than 0, that actually stabilizes the weights. Okay, and so models that might give very similar predictions and then would therefore have very correlated errors on left-out data, basically this says, well, you can use one or the other, but I'm not going to let you keep both. Okay, so it's going to constrain the number of models that appear in there. But again, this kind of looking at it from a decision theoretic perspective allows us to think about things, what had been discovered from frequentist side as stacking. It gives kind of a Bayesian justification for that. Again, we can go further with that. Yes?
Can I ask, so when you do lasso, right, you can really do sparsely. Here it's not clear to me how many actually really go to 0, or if they just get small.
They go to 0. Under the on this, because they have to both, there's two constraints. If we go back, let's see here. So there's not only the constraint here, so if you, again, because they have to be non-negative, you could just substitute the absolute value in there. The sum to 1 constraint really drives them to be, so they have to be small, and then the non-negativity. So you're going to get a lot of them that will actually go to 0 in this case, more so than with a lasso. Okay, all right, yeah, and so again, this kind of fits into the framework of which has been really popular if any of you have ever played any sort of Kaggle competition. There's all the software now for doing like super learning, ensemble learners that are, again, trying to combine lots of different models that wouldn't fit naturally under, say, one likelihood or one model together, okay? And often, you, again, have improved predictive performance. Okay, so just kind of example to show how those weights really go to 0. This was previous work done in terms of ovarian cancer. Again, the goal was trying to predict long-term versus short-term survival. And so there were, again, retrospective samples. This is not anything in the era of big data. So again, we have about 54 observations here. But there are lots of different predictors. So there were different combinations of genes. There are other clinical variables. And so at this point, different classes of models. Some of these were based on tree models, okay, so just looking at models based on only the clinical predictors. There were models that used all of the expression data, okay, so again, additional trees from that. Linear discriminant analysis is another approach, and so again, if you think about these models here, these were kind of prospective logistic-like models. The linear discriminant models involve a completely different likelihood. Okay, and so it's not feasible to actually have one kind of model that would encompass both of those at this point. Okay, and so again, if we use from these combination of weights, we can find the weights using all the long and short-term survivors, so under those sum to 1 constraints and non-negativity. And so here's just kind of a blow up. If you do nothing, okay, so the weights are unconstrained, the scale here is going from -40 up to 40. Okay, so again, some of these models are giving very similar predictions. We don't really need all of that collection. And so if we actually force the weights to now sum to 1 and are non-negative, then we can see that there are a number of models in the blow up here that are now set to 0. So we're getting rid of those redundant models. And then the weights here are, again, have greatly stabilized. Okay, so it's a very strong kind of constraint on building those models or changing the weights. I'm just going to skip over that, I think. Okay, and so again, with the classification, what we find though is that by doing this averaging, we do better than any of the individual models on their own. So again, this is kind of similar to a lot of the experience that people have used other types of ensemble methods. And same thing with just even the Bayesian model averaging in the M-closed case, that by using multiple models, we can often do better than any single model will at the predictive accuracy. So comments on this. So in some sense, one can relax that sum to 1 constraint. And in fact, one can actually show that if one chooses the models that go into that ensemble really poorly, okay, the sum to 1 constraint can actually lead to inconsistencies, okay? So there was nothing in the original work say of Bryman or Wolpert that said that there's a theoretical justification for having those weights sum to 1. If we looked at it as an ensemble approach, you might say, oh, okay, I'm adding up this combination of models. They look like kind of probabilities. It seems natural that they should sum to 1, but it's not imposed at all in the problem. It's an external constraint that we're putting in there. And so if your models are really biased in some ways, then this sum to 1 constraint can actually hurt you. Okay, so again, like with lasso, it's basically the absolute value has to be less than some constraint, say t. T is usually not 1. Okay, and so there's some flexibility in that we may be able to relax that constraint and still do better. Okay, again, absolute value. Yes. Okay, so in this case, if somewhere over here, the true state of nature, the oracle is speaking to me, so if I were to think about, I know what the truth is, okay, if I were to, so basically by using this ensemble, all I'm guaranteed is that I'm trying to get close to the truth. It doesn't say that I'll ever actually get to the truth. So if I'm thinking about, like, if I knew the true parameters, if I knew what the true say mean is, can I actually recover that if I have an infinite amount of data? Okay, so in the asymptote. How do I define it? So in this case, whether or not that distance between, say, what I'm predicting and the truth, can that distance go to 0 in some probabilistic sense? Okay, so this may be in asymptotic samples there. So depending on what our utility is, can I recover the truth in this case? Okay, so and another thing you might think about is that, well, I was using squared error loss. What if I had a different utility function? So for everything that I want to do, if I have a different set of inputs, would I end up with different weights? Okay, and so the question is, what happens with other decision problems? Do I need to redo this all over, or do I need to think about maybe a bigger problem here? Okay, and then last of all, while this allowed us to come up with, say, a point estimate, what happened to our uncertainty quantification? Okay, so I have one estimate out. I might want to look at quantiles. I might want to think about the whole distribution. All right, so again, more general utilities. So there's a recent article that's in Bayesian analysis that is looking at kind of a wider class of utility functions. So under our square error loss, we only have optimal point predictions. Okay, so they're going to be close to that true generating process. But we might think about, again, instead of just stacking predictions, stacking probabilistic forecasts. And again, this also goes back to the original articles by Wolpert, in which case now our action is, rather than having just the point predictions, we could actually stack distributions. Okay. And so if we take this framework, where now I'm going to try to learn the optimal weights, in this case, one can actually solve this problem by basically kind of like an EM algorithm, and now the weights naturally sum to 1, okay, in this case. So there's no external constraints. One does get a solution where the weights will sum to 1 and will be non-negative from that. Other types of utilities, we might want to use, again, proper scoring rules to define so that we can get kind of unique estimates. And so the negative quadratic loss is proper, but not a strictly proper scoring rule. Okay, and so we may not end up with unique weights. If we actually look at, say, logarithmic score, then we can end up having kind of unique weights that come out from this problem. All right, and so there's been also work in terms of probabilistic forecasting. So if you go back to some of the work of Adrian Raftery and co-authors from 2005 and going forward, of what they describe as ensemble BMA. Okay, and so that's, again, using this kind of logarithmic scoring rule to try to combine models, combine forecast from that. Okay, and so again, their formulation is, again, trying to find the weights. They actually have another parameter in here, say a sigma squared, that's within each model. So they're postulating, again, some model for, again, the data. This is going to be kind of this weighted average then of these different densities in there. So each of these could be under predictions. These YIs are coming from the different forecasts. In this case, it's slightly different that these forecasts are not being learned from the observed data, but are given external. And so that may be more similar to many of the kind of computer models where, again, there's a deterministic or maybe stochastic, but we're not updating information or learning that model in the same process where other cases have evolved of trying to both learn the models as well as the weights simultaneously. So in this case, the weights or the model predictions are given externally, and now we're using the observed data to try to find the weights that would allow us to combine them. Okay, so in their case, they're using Gaussian distributions, and a key point here is to realize that by doing this kind of weighted combination, that these models might be biased. Okay, and so in this case, they're trying to take account the bias by basically doing kind of a regression of looking at the future observations, regressing them on the, or taking the predictions and regressing them on the future observations. So this allows for both the bias and calibration of the model, and again, is learning kind of a common variance sigma squared to try to build this model. Now, this looks a lot like a mixture model, okay, for those that are familiar with it, but it's not, okay? And so, and again, if there's time, there are kind of key differences between the models here, and so in the mixture models, basically all of the data are being used to inform the means in each of the components, while in a mixture model, you might be only using subsets of the data to inform the means in those components. Okay, but there's similar algorithms that can be learned, that can be used to learn those weights as the mixture weights. In their point, the weights can actually evolve over time, and so that may be something where we'd like to have not just kind of static weights, but dynamic weights. Okay, and then look at, again, multivariate outcomes. So it may be that we're not just going to focus on one component, one response. We've got multiple responses that we're interested in trying to predict. So it might be just both temperature, say rainfall. There may be other, again, multivariate outcomes that we're going to look at. Mike West and co-authors have kind of looked at similar problems. And this is from more like dynamic linear models. This is coming more from the kind of economic forecasting approach. But it's also the idea of trying to build a model where the weights could evolve over time. Okay. And again, there can be Gaussian process emulators for computer models, statistical models. Those might be some of the building blocks that one might want to use in kind of coming up with the models that are in here, okay, instead of just the simple kind of Gaussian distributions. Okay, so I'm going to probably start early, leave time for a discussion or for more coffee. But what I've tried to do is at least give you kind of an overview of kind of the kind of model averaging for uncertainty quantification under some of these different perspectives. So one of the things that you might want to say is, like, if you think about like the M-closed perspective, you know, while you might be able to do stochastic expansions, there's always the question of, well, if you know a lot about the system in terms of computer models, you know, that doesn't necessarily give you a good way to kind of combine that. And so the M-open perspective, where you can use a lot of the science and math that's been built up, seems to be a more reasonable approach for trying to build these kind of ensembles from that. Okay, so you don't want to throw out all the mathematics. I guess even when I was like as an undergrad, one of the reasons I got interested in statistics was trying to look at models based on differential equations that might predict how trees grow. And of course, when I went back to the stat department to say, well, you know, how can I fit these models? Oh, they said, just do a polynomial regression. It's like, well, wait, we know a lot more about the structure there. Let's use that. And now let's try to, in this case, let's try to build maybe better ensembles from that. There is the approach in here. There seemingly is a kind of dependence on the choice of utility functions. If we use this logarithmic score, that gives us a case where the weights are always non-negative, and so that might be beneficial if we think about that. Squared error loss is allowed, can get point estimates. The proper scoring rules often give us kind of a global estimate if we think about that in terms of estimating a distribution. But that might be sensitive, and I don't know, again, this is kind of an open question, is how sensitive is that to the kind of forms of those models that go into the mixture components? Okay, so if we're using simple Gaussian distributions, that might end up constraining us in certain ways. And so maybe we should kind of step back and say, well, we could formulate things by looking at both squared error loss, but also look at, say, select quantiles. Okay? And so that might, again, kind of step back to say, well, maybe we can't get one kind of mixture model that gets everything perfectly, but by focusing on the key quantiles and other point estimates, considering that as kind of multiple objectives, we could also simultaneously learn weights in that case. So it might be something intermediate between just the unstable point estimates under squared error loss and the more kind of global solution where we're trying to learn those kind of weights that are going to work well for both the center of the distribution as well as the kind of extreme quantiles of the distribution. Again, there's a lot of connection in these approaches to mixture models. They look a lot like mixture models, but they're not quite there. And so particularly when one starts to understand like how the estimation approach, you can see some of the key difference there. But there's a wealth of information on how do we combine models from experts. And so some of that might be informative in terms of advancing what's going on with these ensembles. Okay. If we're thinking about trying to learn these weights, in a case where we're learning both the models, aspects of the models, uncertainties about the models that go into the components, then there needs to be some sort of framework of kind of keeping it honest so that there's a certain amount of data that's used to learn the models and then another set that's used to kind of update the weights from this decision theoretic perspective. By computer models where the outputs are more deterministic, there's not that extra complication and that actually can simplify our lives there. One of the things that I think would actually be very interesting to follow up on is that how allowing the weights to actually depend on parts of the input space. Okay, so there may be certain models that do much better in certain cases than in others. This framework doesn't actually allow that. So by having the weights, in the case of extending for graph tree, the weights would be allowed to vary over time. Okay, you can think of time as one of the inputs, but maybe there are other parts of inputs that go into the, say, computer models, and we'd like to be able to use, say, different models from that. Can the weights actually tell us anything about which models are doing better or worse? Okay, and so that would be something that I think could be useful to follow up on and help us to maybe build better emulators from there. Okay. Incorporation of model complexity, regularization, and utility. So just from the point estimation approach, that sum to one constraint is rather artificial. Other approaches in terms of utility build that in as part of the solution. Okay, so while it's enforced, it's not necessarily, that can also lead to problems with the consistency. So we need to be aware that if the models are biased, okay, kind of garbage in, garbage out. And so, again, thinking about how do we calibrate the models, we still need to correct for bias by taking this ensemble approach. Okay, and then again, there are lots of challenges here for kind of computation, so optimization. Some of these fall nicely under quadratic problems or convex problems. There's EM algorithms that can be used to find some of the solutions, but then also it may need to look at like variational Bayes methods or approximate Bayesian computing could allow us to kind of learn weights in maybe more flexible scenarios in there. Okay, so I'm going to stop here and hopefully there's, again, time for questions or coffee. So, good.